Bismillahirrahmanirrahim. In this video, we are going to discuss some methods for the computation of state transition matrix. In the last video, we have seen that we can determine the state transition matrix using this equation. That is the Laplace inverse of Si minus A inverse. Right. So what is this A? This is obtained basically from the state space representation of your system. We know that x dot t, that is equal to a into x of t plus b into u of t, where this u is your input and this is the vector of the state variables. B is the input matrix and A is the state matrix. So this state matrix A is of order n cross n, where n are the number of the state variables which are used to define your system. So if you know this matrix A, you can determine the state transition matrix with the help of this equation. State transition matrix is the one which helps you to determine the response of your system at any time t given the initial values of the state variables and the input. So state transition matrix, as discussed in the last video, is given by this equation. The second method which is used to determine the state transition matrix will be discussed now. If a matrix A can be transformed into a diagonal matrix, then the state transition matrix is determined with the help of this equation. Let me call this is equation 2. So what is P in this equation? P is basically the diagonalizing matrix for A. So if you can diagonalize the matrix A, then with the help of this equation you can determine the state transition matrix. So in this e power dt, this matrix will be given by this equation. These are the terms at the diagonal of this matrix, and in this lambda 1, lambda 2, lambda 3 and so on up to lambda n, these are the eigenvalues. So these eigenvalues are obtained from the characteristic equation of your system. So characteristic equation of your system is Si minus A. So the roots of these characteristic equations are the eigenvalues. So let's suppose that for a system of order n, there will be n eigenvalues. So these eigenvalues are basically the closed loop poles of your system. So first step is to determine these eigenvalues, and with the help of these eigenvalues you can define this matrix E dt, exponential matrix, right? So from eigenvalues, first step is to determine this exponential matrix. Once you get this matrix, then this diagonalizing matrix is obtained. So this diagonalization matrix is obtained with the help of this equation, that P is equal to this one. First row consists of all ones, then the second row consists of the eigenvalues, the third row will be the square of all of those eigenvalues, the next row will be the cube, and so on. The order of this matrix P depends upon the order of your matrix A. Right? So for a 2 cross 2 matrix, this matrix P will be given by this equation, that is 1, 1, lambda 1, lambda 2, because there will be only 2 eigenvalues and these eigenvalues must be distinct. For this equation, for a 3 cross 3 matrix, this value P will be given by this equation. 1, first row will be consisting of 1, second row will be the eigenvalues, and the third row will be the square of these eigenvalues. Right? And similarly, for the order of 4 cross 4, you can add one more column and row. So you are going to obtain this diagonalization matrix with the help of this equation. Let me call it equation 2. So if you have this matrix P and exponential matrix dt, so you can find out the state transition matrix, which is the exponential matrix of A. So now let's consider an example to look at in detail about these two methods. Let's suppose that the state matrix A of your system is given by this equation. So we are supposed to compute exponential matrix by using the two methods which we have discussed above. So first of all, let's define the characteristic equation lambda I minus A. So this is the identity matrix. So for a 2 cross 2 system, for a 2 cross 2 state matrix, the identity matrix is this one. So multiplying it with the lambda, so we can write this like this, minus A, this A is given to us. So our lambda I minus A matrix will be given by this one. So now the roots of this one, the determinant of this one, lambda I minus A, setting it equal to 0, that will be the characteristic equation, and the solution of that equation or the roots of that equation will be the eigenvalues. So the eigenvalues can be obtained with the help of this equation. So determine the determinant of this one, lambda into lambda plus 2 minus 0, setting it equal to 0. So solving it for the lambda, lambda is equal to 0 or lambda is equal to minus 2. These are the two roots. Now we know the roots, now we can find out the matrix P. So matrix P will be equal to 1, 1, lambda 2. So from here I can write this is 1, 1, 0, minus 2. So this is matrix P. And the second thing that we need to determine is E dt. So that is given as E lambda 1 t 0, 0, E lambda 2 t. So from this you can determine this exponential matrix T. Okay, now using this equation, you can see that we can find out this matrix E dt. We know the values, eigenvalues. First eigenvalue is 0, so e raised power 0, that will be 1, and the second eigenvalue is minus 2, so e raised power minus 2t. So this is our exponential matrix E dt. And this is our matrix P that is obtained from this one. And this is P inverse. So we have seen above that state transition matrix, that is e raised power at, that is given as P into exponential matrix E dt into P inverse. So this is our matrix P, this is matrix E dt, and this is P inverse. So solving this equation, we can find out the state transition matrix. So state transition matrix, if you simplify this one, will be obtained by multiplying these three matrices. This is the inverse of this one. So if you simplify this one, so you will get this matrix. This is the state transition matrix. And if you know the initial conditions, by multiplying with the state transition matrix, you will get the response because of those initial values. Or if you know the input, then multiplying that input with the state transition matrix and then integrating over the selected interval of time, you can find out the response because of the input. That is the forced response of your system. So with the help of this state transition matrix, you can determine the response of your system. So we have seen the method, that is this equation, P into e raised power dt into P inverse. With the help of this equation, you can determine the state transition matrix. So we have obtained this equation. Now let's check the other method that we discussed in the last video, that how we can get the state transition matrix from that one. So for that, again the characteristic equation is required. It is Si minus A. So we are given with the matrix A, the state matrix, and Si is this one. So if we simplify, we are going to get this matrix. Now taking the inverse of this one, so inverse of this matrix will be this one, right? So once you get the inverse, then we know that Laplace inverse of Si minus A inverse is basically your state transition matrix phi t, or e raised power at exponential matrix. So if you take the Laplace inverse of this one, you will get the state transition matrix. So Laplace inverse of 1 by s is 1. So Laplace inverse of this one, you can first make the partial fractions and then you can find out the Laplace inverse. And for this it is 0, and the Laplace inverse of this one e raised power minus 2t. So this is the state transition matrix. Using this you can find out the state of your system at any time t, provided you are given with the initial values and the input. You can look at the initial response and the forced response of your system. So here you can see it is exactly same what we obtained from this method. Either you can obtain state transition matrix using this equation, or you can determine the state transition matrix with the help of this equation. Both methods are equivalent. They will give you the same result. Now let's look at another example. Let's suppose that we want to determine the state transition matrix for a system whose state matrix is this one. So let's first of all find out Si minus A. So Si is this part and A is this one. So if we simplify, we are going to get this equation. Now let's find out the determinant of this equation. So that will be equal to s plus 3 into s plus 4 minus 0. So we will get this equation, that is the determinant. Okay, and to find out the inverse of this one, we need the adjoint. So how to get that one? Swapping these two terms and changing the sign of these two. So you will get this matrix. This is the adjoint. So adjoint of this matrix divided by the determinant of this one, you will get the inverse. So this is the determinant that we are going to have from this equation, and dividing this matrix with this one, you are going to get the inverse of this matrix Si minus A. So once you get this one, here you can see s plus 4 divided by this one, so this 2 will be cancelled out. This is 1 by s plus 3, 1 divided by this one, and then 0 divided by this will become 0, s plus 3 will be cancelled out, 1 divided by s plus 4. So this is our inverse Si minus A inverse, this part, right? Now if you make the partial fractions of this one, you can represent it like this. Okay, now the Laplace inverse of this equation will be the state transition matrix. So we are going to take the Laplace inverse, and for that we will have to find the Laplace inverse of each term. So Laplace inverse of this part is e raised power minus 3t. Laplace inverse of this one, for this part it is e raised power minus 3t, and for this one it is e raised power minus 4t. And for this it is 0, and for this it is e raised power minus 4t. So this is our state transition matrix. Okay, now let's look at another method that is based upon similarity transformation method that is used to determine the state transition matrix. So I will first of all go through an example, and then we will define the steps which will be used to determine the state transition matrix using the similarity transformation. So let's suppose that we have this state transition matrix, state matrix 0, 1, minus 2 and minus 3, and we want to determine the state transition matrix. So first step is to define the characteristic equation, that is lambda I minus 1. So this is lambda I, lambda I minus A. So this is lambda I, this is the equation matrix A. So solving this, you are going to get this matrix. So if you set up the characteristic equation, that is the determinant of this one, and you find out the roots, so the roots will be minus 1 and minus 2. These are the eigenvalues of the system, representing the closed loop poles of your system. Eigenvalues are the closed loop poles. So in this first step, we are going to determine the eigenvalues, right? Okay, so after determining that one, you are going to define the eigenvectors. So the given system is of order 2 cross 2. So there will be two eigenvectors. So the first eigenvector, let's suppose that is p1, that will be consisting of these two values p11 and p21, and the second eigenvector, that is p2, will be equal to p12 and p22 for a system of 2 cross 2. If you have a 3 cross 3, then p11, 21 and 31 will be there, p12, 22 and 32 will be there, and then there will be the third eigenvector as well. But for over here we have the 2 cross 2 system, so two eigenvectors will be defined. Now the next step is to determine these values. So these values are determined by solving the characteristic equation for the eigenvalues, multiplying it with this eigenvector, that should be equal to 0. So first of all, let's this eigenvalue. So now for this eigenvalue, that is minus 1, first of all we need to determine this, we need to evaluate this equation, that is the characteristic equation at this particular value of eigen value. So first of all we are going to determine this one. So how to get this one? We are going to solve this equation A, that was this one, that is lambda I minus A. So we are going to solve it for our first eigenvalue, right? So minus 1, and this is minus 1 plus 3, so that will be equal to 2. So from here we will get this matrix minus 1, minus 1, 2 and 2, that is by solving this matrix at the eigenvalue, that is equal to minus 1. And now taking this eigenvector p11 and p21, the product of these two should be equal to 0. So we have set up this equation. Let's suppose this is equation 1. So now if we solve this equation, we can find out p11 and p21, and we can get our eigenvector, first eigenvector. So from this set of equation we can write down these equations, and if we solve these two equations we will get p11 equal to 1 and p21 equal to minus 1. So we have obtained the first eigenvector with the help of this equation. Now we are going to get the second eigenvector with the help of the second eigenvalue, that is lambda 2, and that was equal to minus 2. So again using this equation A, first of all we will have to get this lambda I minus 1 for this eigenvalue, so that will be equal to minus 2 minus 1 to minus 2 plus 3, so that will be equal to 1. And multiplying this one with this eigenvector p12, p22, we should have this one equal to 0. So this is our equation, and from this equation we can find out the second eigenvector. So that you can see over here that we are setting up this equation. This is obtained by solving equation A using lambda is equal to minus 2. This is our second eigenvector, setting it equal to 0, and then solving this equation we can find out p12 and p22. Once we know, it means we know about these eigenvectors. This is determined and this one is determined. So in the step 3 we have determined the eigenvectors. Now in step 4 we are going to define the matrix M, which is obtained by these eigenvectors, which we have obtained above. So our first eigenvector, you can say this one p1, P1 is equal to 1 and minus 1, and the second eigenvector, that is 1 and minus 2. So using these two, you can define the matrix M, that is the obtained then from these eigenvectors P1 and P2. Depending upon the order of system, let's suppose that if the order is I, then the matrix M will be obtained with the help of this equation. Over here we have the 2 cross 2. We have only 2 eigenvectors, so our matrix M will be given by this equation P1 and P2. So P1 is this one and P2 is this one. So from here we are going to get the M inverse, that is given by this equation. And the step 5 is to determine the state transition matrix with the help of this matrix M that you have obtained in the step 4. So this equation is used. This is exactly what we discussed in the previous case, right? So this is basically the diagonalization matrix. Okay, so M is this one, M inverse is this one, and this is the matrix EDT, which is obtained from the eigenvalues. Over the diagonals you can see this is e raised power lambda 1t, lambda 1 is minus 1, so it is e raised power minus t, and the second eigenvalue, that is lambda is equal to minus 2, so from here you can get e raised power lambda 2t, that is equal to e raised power minus 2t, and that you can see over here. So these two are obtained from the eigenvalues. This is the diagonalization matrix, this one and this one. This is M, this is M inverse. So multiplying all of these together, you can get the state transition matrix. So that is given by this equation. So this is EAT. So if I summarize, the first step is to determine if I go back and make a summary, so first step was to determine the eigenvalues, right? So let's summarize over here. First step, determine eigenvalues. The second step is to define eigenvectors. The third step is to calculate eigenvectors using eigenvalues and this equation. Once you determine the eigenvalues, the fourth step is to find out the diagonalization matrix M. M is determined using the eigenvectors, right? So M is given by this equation. Once you determine this diagonalization matrix, then the fifth step is to obtain the state transition matrix with the help of this equation. So these are the 5 steps which you can use to determine the state transition matrix. So this is the similarity transformation method. In this, you will be using 5 steps to determine the state transition matrix. So if I summarize this video, we have discussed different methods for the evaluation of the state transition matrix. That's all from this video. Thank you very much.